My name's Jason Davidson. I'm Director of Engineering at Figure, and I work on the blockchain team. Today, I'm going to talk about our Provenance blockchain ecosystem and what we're doing in the financial services industry. A little background, Figure is a financial services company. We are leveraging blockchain to remove some of the friction that we typically see in financial services, as well as eliminate some inefficiencies in that area. So today, what I'll do is I'll be talking about our blockchain product, showing you, most importantly, how blockchain is helping Figure do some pretty awesome things. We start off with, I've been at Figure for almost a year and a half. Figure started last January as a startup. I think I was engineer number 3 or 4, and this was in February of last year. We decided to go down to San Francisco to meet the CEO, the C-level executives, talk about what we want to do at Figure, and went down there with a couple of coworkers, and we were having lunch. It was a taco bar. It was phenomenal. And we sat down, and there was one extra chair left, and we were eating our tacos, and the CEO of the company, Mike Cagney, came and sat down next to us and started talking to us, asking about our backgrounds, what we were interested in doing, why we were at Figure, that sort of thing. And the conversation ultimately turned to me and said, so what do you think of blockchain? And I looked at him, and I said, blockchain is just a bunch of hype. And he stopped, he paused, mid-taco, looked at me like, who the hell is this guy? A, and B, does he realize what we're trying to do here? So at the time, blockchain was a lot of hype. I still stand by that blockchain is often a lot of hype. But today we're going to talk about how we bust through that hype and how we build a real live production blockchain system for financial services. So let's start with, what is it? If you're familiar with Ethereum or Bitcoin, you're probably familiar with a cryptocurrency, with a public blockchain network where anybody can download it. You've got some certificates, some keys that you can do business on Bitcoin or Ethereum. Provenance and the Provenance ecosystem is a little different because we serve the financial services industry. We do things in a private, permissioned, and consortium-based way. And what that means is there's a central Provenance administrator who's responsible for onboarding and vetting members, organizations, nodes that come on and wish to participate in the consortium. Because we have certain requirements in our space like KYC AML, which is Know Your Customer, anti-money laundering rules and regulations. So when we think of what we've got for Provenance, it's distributed and it's available only to onboarded investors, members, nodes, organizations. You probably heard the term smart contracts. Unfortunately named, they're not so smart. We'll look at one at the end of the slideshow here and you'll be like, that's it. But what those are is they're the agreements that the members use to conduct business with each other. It's almost like, think of it as like digital legal pros in a sense, that before we ultimately provide truth or put truth into the blockchain, we have to have some mechanism to do that. That's what smart contracts do for us. So if we look at what we have for Provenance, there's basically 4 members that are involved, or four entities that are involved. We have a central administrator who's responsible for that onboarding, the governance of the platform. Provenance itself, the goal is it won't be owned by Figure. We're gonna set it free, man. It's not gonna be owned by anybody. So this central administrative console is very important. That's the governance board for Provenance. Members, again, are those financial institutions who are conducting business, investors, banks, securitization, all those types of people who do business on Provenance. And then the nodes are who are actually hosting the underlying blockchain technology. That's where the data lives. That's where the truth lives. It's all of these nodes. They're disparate in role and they're disparate in where they live within the country. Finally, something that differentiates Provenance from other blockchain platforms or ecosystems is this concept of an omnibus bank. If we think about what we do in financial services, the basic premise is we're taking some value. We're originating loans. We're putting those loans on the blockchain. We have to have some mechanism to move money when we originate a loan, from the loan originator, from the bank, to the borrower. With an omnibus bank and the omnibus bank solution that we have, we can do near real-time settlement of those funds. So if you go out to figure.com and you try to get a loan, you'll see that we do it in 5 days, right? That's our claim to fame, is a 5-day turnaround on a home equity line of credit. If you're familiar with home equity lines of credit, it's 45 days with your bank. So that omnibus bank is what gives us that bridge between the value represented on the blockchain and the movement of money and memorializing on the blockchain. What does it do? What does a blockchain do? Just a dumb data store, just a slow database. What it really does is it provides trustless data immutability, and that information is distributed. Trustless data is kind of a nebulous term. It gets thrown around quite a bit. What it means to us is I don't have to set up amongst the members in the consortium this trust commitment. I don't have to commit to trusting these other members. I don't even have to commit to trusting their data. But I do have to trust something, right? So where we come in with Provenance is we trust these smart contracts. So given organization A, who I don't trust, their data A, piped through some smart contract, the resulting B of that smart contract is the truth. We all agree that the truth is B, therefore it's trustless data before it comes in or at conception. Immutable, obviously, can't be changed. Once you put data on the blockchain, and I'll describe the data structure underneath this, it cannot be altered. We'll leave it at that. It's distributed. So if you were to try to alter this data on the blockchain, you'd have a very hard time altering it in all of these distributed nodes. So we take this immutable history, we distribute it to the multiple nodes in the ecosystem, and we'll talk about consensus and those sorts of things, but there's no one single truth of the data on the Provenance blockchain, and nobody owns that data on the blockchain. So why does it matter? Well, for what we do in financial services, think of financial services if you're not familiar with it. It's just economic services. It's things like consumer finance, capital markets, securitization of loans. It matters because we can eliminate inefficiencies in this sector. Figure saw early on how we could do that. Trust is a prominent issue in the financial services, and that's what blockchain is about. So we can take trustless plus immutable plus distributed, combine that with a ledger, a registry, an exchange to track these assets that we're putting into Provenance, and we end up with this frictionless financial services platform. Something that we've done, we believe in this so much that we actually built a lending platform to prove that blockchain is viable in our space. So when you go to figure.com to try and get a HELOC, you're using the lending platform that we built to prove that blockchain works in this sector. So what does it solve? So $3 trillion is what it solves. That's a big number, right? So financial services has had a long history of cost and inefficiencies. If you think about all of the loans that you've ever obtained, a home equity loan, a car loan, what happens is that companies take these loans, they pool them up, the interest that's paid each month on this loan is a security, right? So it's a vehicle to make money on all of this interest that comes in. That's what securitization is. So in order to do that, though, in order to trust what we're doing in those securitization pools, we have what we call rent seekers, custodians, rating agencies. We've got aggregation costs. We've got all these people that want their hands in this mix because they charge a fee to make sure that the data that you're putting into the securitization pool is trustworthy. So again, figure early on said, all right, well, let's eliminate all these people, and what does it look like cost-wise? $3 trillion annually is what it looks like cost-wise. So instead of paying these external rent seekers, as we call them, just pay us a small fee instead. So blockchain eliminates these processing inefficiencies, it doesn't eliminate processing inefficiencies. You'll read that blockchain is slow. We even countered that too. Blockchain is slow. You think about what it's doing and how it's distributed. There's no quick way to query information out of a blockchain. But the savings that we get when we eliminate the human inefficiencies, these rent seekers, that's our value proposition. All right, we understand the what, the why. Let's talk about how this thing works. What is a blockchain? So really, I love to say this, but it's so true. Blockchain is just a dumb linked list. That's it. If you remember your linked list data structure from high school, college, whatever, that's all we're doing here. We're just linking blocks. It's a chain of blocks. It literally is a blockchain. The way that it works is if we look at block 1, block 2, block 3, we've got facts. Facts is our domain model, the things that we're conducting business upon. We take those facts, we use a cryptographic hash of those facts, and we run that through the hash, and we come up with a block hash, so that feed face at the bottom there. We take that block hash, and when we write new facts or new information in block 2, we take feed face and add it to the header of block 2, along with our additional new facts, hash that up, and come up with a new hash, cafe babe. And then finally, when we get to block 3, we do the same thing. So what this means is, if I were to try to change any of the facts in block 2, I would also have to change the hash of block 2. which means I have to change the hash in the header of block 3, which means then I have to change the hash of block 3 because the header hash is included in that hash. It's just not feasible to do that. You could do it, but we'll find out why it's difficult to do next. As soon as we distribute that blockchain, then it's very, very infeasible to modify that. It's an immutable ledger that's distributed to all these nodes. It's just that linked list. Those hash values, that data in that linked list are distributed. Within Provenance, when we distribute the information or we distribute our blockchain to our nodes, we use Kubernetes. The Provenance platform is running on GCP, AWS, Azure in different regions throughout the country. We have 12 nodes today in production, and that's how we get that distributed immutable ledger. So then the question becomes, well, I need to change data on the blockchain. It's dumb if I can't. Well, it's append only. It again is that append only ledger concept that if I want to add information to the blockchain, I have to create a new block. I have to ask all of the nodes in my network to also create that block. I have to ask all my nodes to consent to that block creation. So we come up with this huge ring of trust here to add new information to the blockchain. So let's distill the hype. So when we started looking at blockchain solutions last year, there was a lot of buzzwords. There still is a lot of buzzwords. There's a lot of technology here. And I don't want to do hand waving and say, oh no, it's super easy. It's not. There's a lot of things going on behind the scenes, not only in Provenance, but any blockchain platform. But as we started to look at what we really needed to build, 5 primitives emerged. And those 5 primitives are identity. We need to reliably and accurately portray the business members in our consortium. We need to have some identity. Facts. We need some business data. We need some truth. We need some state about that data. And we need to represent it somehow. Smart contracts. Again, we need some sort of executable contract language that these identities can use to trade these facts. To perfect business transactions amongst themselves. That's what smart contracts do for us. Consensus. Because we're distributed, we need some mechanism to say the information that I add to the blockchain is correct, it's consistent, it meets all of the signature standards that we require, all the endorsement policies. Our consensus algorithm and our consensus cluster does that for us, and I'll talk about that in a moment. Finally, we need privacy. If we think about what we're putting on the Provenance blockchain today, it's financial information, it's loan information, there's protected information there, social security numbers, information about people's properties and names and dates of birth. But not only that, the nodes themselves, again, because they are disparate in role, they could be competitors. So the information that I'm placing on the blockchain that's getting distributed to all of these nodes in the consortium, they could be competitors. They could be looking at loans for their competitors. So we need some sort of privacy mechanism to protect that information that we put on the blockchain. So let's drill into our 5 primitives, starting with identity. The Provenance administrator entity, like I said, does all the onboarding and the KYC AML for the member. When they've done that, what we do is we issue them a member enrollment certificate. Everything in the Provenance network has a member enrollment certificate. That certificate is just standard X509 cert. Applications, systems, people like originators or investors who are using it, all have a certificate. That certificate is rooted from an intermediate cert all the way back up to the Provenance root CA, Certificate Authority. In addition to that, not only do we issue member certificates at this level, but we can also issue certificates to organizations themselves, those other nodes, such that they could start creating members themselves and invoking smart contracts using those members. What that provides us, again, is that chain of trust all the way up to the top. So your identity is your certificate, and everything in the platform has an identity. Certificates are used for signing transactions, invoking chain code, mutual TLS, connectivity, endorsing transactions. Everything in the ecosystem has a certificate. System, person, machine, application. So digital signatures are a very important component of what we do. We need to sign and verify facts. We need to know that if Alice signs some fact, that she is in fact allowed to do that, that she has a proper certificate to do that, and that Bob can use the Provenance Public Key Registry to validate that Alice actually signed this fact. Digital signatures provide that guarantee on the integrity of the fact. It is our trust commitment, right? It is that we are trusting all of the members are using the correct certificates and are allowed to do signage on the platform. Smart contracts. Really what we needed to do here was just get more lines on a slide, so that's why we have this one. Smart contracts themselves, again, it's just, think of it as just digital legal prose. It's just a common set of contracts, a common set of code. It's just business logic. We're familiar with business applications. That's what a smart contract is. It's just a business process. Something with regard to smart contracts is they don't actually change the state of the ledger. The smart contracts, when an investor says, hey, I want to onboard this loan, we'll run the onboard loan smart contract. That smart contract's purpose is to propose a change to the ledger. Consensus is what actually commits that change to the ledger if it's valid. So that's an important distinction here. So again, smart contracts read proposed changes to the ledger. Smart contracts themselves are signed, verified, and endorsed by administrators and also stored in the ledger. It's kind of like the C compiler root and C type thing. Smart contracts ensure that when they run on node A, node B, node C, that they have the same read set, which means that they're reading the same data from the blockchain. They have the same write set, which means all of them must come to the same conclusion. And they must concur that the signatures and everything else with regard to that smart contract execution is valid. Finally, smart contracts are bound to an endorsement policy. So to onboard a loan, for example, requires that you run that onboard loan smart contract on organization A and organization B nodes. You have to do that. The consensus will not commit that block to the blockchain until it meets that endorsement policy. Data privacy. What does it mean? Well, we're using an elliptic curve cryptography mechanism to allow members to encrypt their data before it's submitted to Provenance. This means that Provenance, the network itself, has no access to the clear data, except for one small caveat. Members create the keys and manage their keys themselves, and they're encrypting this information, submitting that encrypted data to Provenance. Provenance is then decrypting that information and processing it during smart contracts. So if you think about what smart contracts have to do, they have to take that encrypted information, open it up, run the smart contract rule, pack it back up, store it on the blockchain. So, how do smart contracts do that? How does this all work? Members themselves can share the information with other members. Well, let's talk about Provenance ECIES, which is Elliptic Curve Integrated Encryption Scheme. It allows members to encrypt information, share that encrypted information with other members, Alice and Bob, share that encrypted information with a smart contract for processing only. And if you were to take what we've done with our ECIS solution, compare it with Apple iMessages, you'd be fairly certain they ripped us off. Or maybe vice versa, I don't know. Great artists steal, is that the thing? So the Apple iMessage white paper was quite valuable for us with regard on how to protect data. So what's happening here is, like Alice's enrollment certificate, all we're doing is let's just walk through this process real quick. Alice has a public and private key pair for encryption. Alice registers her public key with our key registry. Bob does the same thing. So we've got public key registry. Alice has some fact that she needs to send to Provenance. She takes that fact and she generates a random symmetric key. She takes that random symmetric key and she encrypts her fact. So now we have some encrypted payload. Well, then Alice takes her public key and encrypts that random symmetric key and stamps that on the payload as well. She does the same for Bob's public key. So now Alice and Bob can take their private keys, open up the data encryption key, take that key, and decrypt the payload. So this works great for Alice and Bob. It also works for smart contract processing. Alice is asking to onboard a loan. So she's running the onboard loan smart contract on node A. When a smart contract starts on node A, it creates an ephemeral set of keys. These keys are rotated constantly. So the smart contract will create the same public and private key pair, register its public key with the key registry. And then when Alice uses the SDK to invoke Provenance to onboard this loan, she says, oh, by the way, I'm sending it to organization A, smart contract B. Pulls that public key back. It's a transient key that we can use to encrypt that information. Then when the smart contract gets that encrypted payload from Alice, it can decrypt all of it, run through its rules on the clear data, re-encrypt it, stick it on the blockchain. So smart contracts follow that same process. Smart contracts dispose of the data encryption key after they're done processing. Again, the key pair that the smart contract uses is ephemeral. It lives in memory for a short amount of time, and we rotate those constantly. So finally, we get to talk about consensus. So consensus is cool. If you go out to the internet, you read about consensus, you read about pre-Byzantine fault tolerance, proof of elapsed time, proof of work, proof of stake, modified PBFT, all these fancy things. We don't use any of that. We don't need any of that. So if you're familiar with Ethereum and Bitcoin being public blockchains, they use like puzzle solving and mining and those sorts of things to come to consensus on a block. The first person to solve a puzzle gets to stamp the block. But what happens is multiple miners can come up with the same result. You get divergence in the blockchain. We don't want to deal with any of that. So what we do is we have a consensus cluster that's running. So every time a smart contract runs and proposes a change, it has to send that change proposal to our consensus cluster. Our consensus cluster looks at it, says, okay, is it signed by who it needs to be signed by? Was the smart contract executed according to endorsement policies? Is the data correct? Are the read and write sets correct between all of these nodes? And if so, we consent to that change, and our consensus cluster writes it to the blockchain, and then it gets distributed out. So one thing to note here is that without PBFT or without BFT, how do we handle bad actors within the network? These nodes are, so we, like the small fee that we charge up front for loan onboarding or anything else that you do on the ecosystem, we take some of that fee and we give it to the nodes. We say, thank you for hosting a node. So there's incentive for these nodes not to misbehave because they get paid fees to act as a node. Well, people are people, so there's still a possibility someone's going to try and hack into this node. We've got intrusion detection systems and agents running on all the nodes, on the smart contract containers and those sorts of things. So we can detect when someone's shelled access here, and then we can shut the node off. So we use crash fault tolerance to make sure that the information is distributed, and then we use intrusion detection systems to make sure that nobody's in these nodes, in these smart contracts, sniffing memory or trying to do something they're not supposed to do. So let's talk about a fact flow. So we've got all these concepts flowing around. We've got privacy, we've got identity, we've got smart contracts, we've got nodes, we've got this consensus cluster. It's all very confusing. If we look at the fact flow, it's actually fairly straightforward, the way that we get information into the blockchain. That's what we're trying to do here with this fact flow. So what we have is Alice wants to onboard a loan. She's going to encrypt that loan. And then she's going to ask node A to run the onboard loan smart contract. She's going to ask node B to run the onboard loan smart contract. She submits that off via our SDK. Those nodes run their smart contract, come up with some result. Alice then takes the results and in part 2, or part 3, submits them to the consensus cluster. So when Alice gets the results, it's a packet of all of the read and write sets on each node, what the node suspect, or what the node is going to write as part of that smart contract, and it gets submitted to the consensus cluster. That packet of information, then the consensus cluster unpacks it, says, okay, do we have the valid signatures? Is the person submitting it, Alice, a known identity? Did she get endorsement from node A? Did she get endorsement from node B? Is the information signed correctly? Did node A actually sign it? Did node B sign it? Those sorts of things. So it's just checking that packet for consistency and validation. Did everybody come up with the same result set? If so, then the consensus cluster takes that transaction or those and puts it in a block and then distributes that block to everybody else in the network. So in this state right here, when she's run that onboard smart contract, she hasn't actually changed the blockchain on node A or node B. This guy does it down here after he's looked at it, made sure that it's okay, and distributed that information. Node C wasn't involved at all in the original smart contract implication, but it still gets the data such that the blockchain and all that information is distributed to everybody in the consortium. That's the fact flow. Piece of cake, right? Originating loan, I'm going to do some hand waving here. Think of it again if Alice is onboarding a loan, the reason this diagram exists is just to show how the omnibus bank is involved in this process. So we have this originator member who's proposing a new loan. That originator member is doing that on behalf of a borrower. So in order to do that, it says, okay, I'm gonna need to run the onboard loan smart contract. That smart contract is going to say, okay, I'm gonna onboard this loan. At the same time, the member's contacting the omnibus bank to say, hey, I need to wire some funds into my omnibus bank account so that this borrower can get paid. When they do that, that interaction is memorialized on the blockchain via what we call a settlement token. As soon as this process completes, that settlement token is redeemed from the originator, moved to the borrower gets their money. This is important because, like I said, that omnibus bank account for Provenance is really a differentiator for us because it allows us to memorialize the actual movement of money in the ecosystem on the blockchain. Otherwise, how would we know that Alice got it, or that the originator sent the funds, that the borrower got their money? The memorialization of that transaction and having that omnibus bank there is absolutely critical to us. So some more wire diagrams here. The protocol itself, what I'm just trying to illustrate here is that, our core for Provenance is that blockchain, is that linked list, is the distribution at a mutable ledger. But really, most of the code that we've written is the periphery around that. The things like the governance, the governance, the admin consoles, our servicing application, our market maker application, our marketplace. There's lots of APIs, SDKs, applications that live around that blockchain that need to be there to create this financial services ecosystem that we're going for. So the blockchain, very important, but a very small part of what we actually do with Provenance. So software ecosystem, again, taking a different view of that protocol. The Provenance SDK is typically what a member is able to do. So there's things like, the data encryption and decryption mechanisms that we talked about are all wrapped up in the SDK. Key management, transaction ordering, commitment, invoking smart contracts are all part of this SDK. And then we have the protocol in the middle, which handles things like APIs, the inventing, caching mechanisms that we have, key registry, all of that. And then finally, the blockchain component, again, are those core blockchains, our consensus cluster, actually storing the state of the ledger on the file systems or in the ledger DB, those sorts of things. So there's a lot of software here behind the blockchain and the protocol components. So our tech stack, what do we use? We use all the things, everything.
Bash.
Bash.
We should talk about Bash somewhere.
The amount of Bash that we use is maybe legendary. I don't know. Think of a project that uses a lot of Bash and then multiply that times 100. We use Bash so much for onboarding nodes, just general monitoring of the system and that sort of thing, just bootstrapping generally. But basically what we're seeing here, like I said, we're Kubernetes based. All of the software runs in pods. We're deploying to Azure type applications for APIs and those sorts of things. So we really do use a lot of software. And what I want to point out is just a little nuance here that, Figure and Provenance, Figure isn't a blockchain company. Figure is leveraging blockchain as a company. That's a crucial nuance to understand. We recognize that, blockchain works in our use case. It works great in financial services because of that trust and the complexity of trust. We're not necessarily trying to build a blockchain. We are leveraging a blockchain to remove those inefficiencies, to help eliminate the $3 trillion annually that we see in the securitization space. That's it. Want to look at a smart contract? All right.
No.
I hate you guys. All right, so let me change my monitor here. And then I've got some face punching to do.
Well, you got to make the font bigger.
Is that big enough for you? So we've got some smart contracts. Again, if you follow Ethereum, smart contracts are like this glorious, magical thing. And even the creator of Ethereum said we should have never called them smart contracts because they're not smart. We need some mechanism to fire these smart contracts off. We need data for these smart contracts. We need to handle the results of these smart contracts. They're not just sitting out there waiting to perform something magical. We've got to build that periphery around the smart contracts and execute them. So what we have here is one example of a smart contract, and this is just example chain code written in Kotlin. Kotlin, if you're familiar with, is a fantastic language. If you see anybody with a figure shirt and you want to know more about Kotlin, ask them. This guy right here specifically. The nice thing about Kotlin is you can write very succinct code, and you can almost create almost a DSL-like smart contract in Kotlin. So that's very beneficial. So other smart contract languages, like Solidity or something, are very narrow in scope in what you can do. Because we're using Kotlin, a general purpose language, to build our business rules, we've got to build abstractions and make things more abstract so that we can put some control or some boundaries around what you're allowed to do with Kotlin. So as you can see here, it's fairly straightforward: add information, update information, transfer information on the blockchain. It's just a Kotlin method. That's all that's going on here. Now I'm going to blow your mind a little bit and talk about, well, we also have some TypeScript ones that we are eventually converting to Kotlin. Handwave, we're going to do this, but this is a little more involved. Asset validation smart contract, right? Is the asset a draw? Does it have a parent asset? So on and so forth. If it doesn't meet these requirements, we'll throw a new chain code error. So this chain code is just basic business logic that you would write in any other application, except for the distributed nature and combining all of the results of this chain code together. That's it. Nothing magical about chain code per se. So the next thing that we want to look at is, so what does Provenance itself look like? Here's the admin console. This is our test admin console. We've got a couple of ledgers. We've got 148,000 blocks in these certain ledgers. If we drill into a block specifically, what you end up seeing is information about that block. So going back to our fundamental data structure, the block itself has an ID, has a cryptographic hash. It's got a creator who proposed the block. The creator ID is their certificate. If I decoded that certificate, I would see an X509 description of that certificate. Who they are, their common name, organizational units, roles, all sorts of good stuff. And then the transaction info for this particular block, who endorsed it? I've got a number 3 endorsement count. I can see the nodes that actually endorsed this request. So we click on details a little more. Now we look at the input args to our smart contract. Ooh, boy, what is that? Well, this is that encrypted data. So the smart contract received this data in the encrypted form. And then it was able to process this encrypted data, do some reading and writing and that sort of thing. There's the endorsement names of the nodes that actually endorsed this transaction, their signatures on that data, so on and so forth. So the consensus cluster takes this block, this proposal to write this block, and looks through all this information to make sure that it's consistent, it's valid, that whoever's doing it is allowed to do that. In addition, that's something that's kind of cool that I've always liked about these blocks and the way the smart contracts work in our ecosystem is this concept of read and write sets. And every time you read something in a piece of smart contract code from the blockchain, that gets stamped in a read set. So when you run the smart contract on multiple nodes, the ecosystem takes that read set and compares it to make sure that you are reading the exact same data on node A that you're reading on node B that you're reading on node C. So that's that integrity check to make sure that all of the nodes are in sync with regard to the state of their data. Write sets are the same thing. The ultimate end result of the smart contract is we are writing some asset to the blockchain, right? That write set is what did we actually write? That write set is used again by that consensus cluster to determine whether or not all of them came to consensus to write that block to the blockchain. Finally, my favorite thing to look at is charts and graphs of what is our test blockchain doing. So this is just a demonstration of our chain height, information about all of the Kubernetes pods that are running within our test system. We've got an Azure and GCP and an AWS cluster running. We can see the states, what's our block count for certain ledgers, what's our endorsement transaction block count as well, what's our memory usage on all of these nodes, memory usage on these peers that are running these smart contracts, how long is it taking us to fill a block with transactions, and then how long is our order / consensus algorithm or cluster taking to actually write these blocks and distribute those blocks to and throughout the Provenance network. Finally, members, just real quick, all of the members in the system, again, have that cryptographic material, their certificate, some key information as well. We store all that information inside of the admin console in Provenance. So with that, I'm done. That's blockchain. It's a viable industry.